Good morning, all of you. Welcome to Sri Jayendra Rank Zone. So far we have completed 15 group elements. Now we are going to discuss group 16 elements. So group 16 elements we are going to discuss in this lecture. Let us see now elements of group 16. This is also very important. Group study is similar to group 15 also, same. Like first we'll study general properties, then we'll discuss then we'll discuss uh, two, that is of the first two elements, preparation, properties and uses. So that's why it is similar to group 15 also. So all the group studies similar, all the group studies we have to do the same pattern, and how we get questions also we'll discuss now. So this is group 16 elements. Group 16 elements includes oxygen, sulfur, selenium, tellurium, and polonium. So these are the elements of group 16. So why they are kept in group 16? Because they have 6 valence electrons. These elements have 6 valence electrons. They have 6 valence electrons in the outermost shell. So that's why. So in the outermost shell they have 6 valence electrons. That's why they are placed in group 6. 6 valence electrons. Even we can call the same group as group 6 also. Group 6A. So group 16 or group 6A both are same. So these elements includes oxygen O, sulfur S, selenium Se, tellurium Te, and polonium Po. So these are the elements. These elements are found in O's and metals. The elements of 16 group, the elements of 16 group are also known as chalcogens, ore forming elements. Why they are called as chalcogens? Because they can form in ores. So that's why they are ore forming elements. So that's why they are called as chalcogens. Like in case nitrogen elements are nicogens. Why? Because their hydrates are poisonous in nature. In the same way, these elements are 16 group elements are called as chalcogens because they form ores. From ores, we'll extract metals successfully. So that's why these are called as chalcogens and they belongs to oxygen family. So total how many elements in this group? Oxygen, sulfur, selenium, tellurium and polonium. Oxygen, sulfur, selenium, tellurium and polonium. Now, next, oxygen is the most abundant element of all the elements on the Earth's crust. Even though nitrogen is occupying 78% by volume, but the most abundant element of all the elements is on Earth's crust is oxygen because it is present in the form of in the air it is 21% by volume, and in the sand also it is in the form of silicon dioxide, in the river water also in H2O, etc. Sea water, everywhere oxygen is present. So without oxygen it's very difficult. So that's why oxygen is the most abundant of all the elements on Earth crust. Sulfur exists as gypsum, calcium sulfate, 2H2O, Epsom salt, MgSO4, 7H2O, baryate, Bas. From all these ores, we'll extract the metals. Galena, lead sulfide, zinc brand, zinc sulfide, copper pyrites, CuFeS2, iron pyrites, FeS2, and so on. So sulfur exists in many forms, in the form of ores only, and sulfur exists as gypsum, Epsom salt, baryate, galena, zinc blende, copper pyrites, etc. Selenium, tellurium are found as metal selenides, and tellurides in sulfide ores. Polonium occurs in nature as decay product of thorium and uranium. So, out of all these elements, polonium is radioactive. Polonium is radioactive. So, its properties are stated separately because radioactive element means it will undergo decay. Undergo decay and forms alpha, beta, gamma radiations. So that's why polonium is radioactive. And in this, we'll study about oxygen and sulfur mainly. Oxygen and sulfur are non-metals. Selenium and tellurium are metals. And they're found as metal selenides and tellurides in sulfide ores. I hope it is clear. So this is the introduction, occurrence of group 16 elements. So how selenium and tellurium are found as metal selenides and tellurides in sulfide ores. Next. General properties of 16 group elements. So, like I told you, as I told you, 15 group, how we are studying the same way, we'll study about 16 group. First, we'll study about electronic configuration, that is general physical properties now. Electronic configuration, atomic and ionic radii, ionization enthalpy, electronegativity, and electron gain enthalpy. So what are these? We already know. Now the general electronic configuration of 16 group elements is Ns2 Np4. As I told you, they have 6 valence electrons in the valence shell. So 6 electrons in the valence shell. So that's why their general configuration is they belong to p block, because the differentiating electron, that is the fourth electron, is entering p block. So p subshell. So that's why it is Ns2Np4. So oxygen 2s2 2p4, 3s2 3p4 for sulfur, and for selenium 3d10 4s2 4p4, for tellurium atomic number 52 4d10 5s2 5p4, and for polonium 4f14 5d10 6s2 6p4. So this is radioactive because its atomic number is greater than lead. So that's why polonium is radioactive metal. It's a radioactive metal. It's a radioactive metal. Selenium and tellurium are metalloids. Metalloids. And oxygen and sulfur are non-metals. So please note down all these things. So the general electronic, or the outermost electronic configuration of group 16 elements is NH2 NP4. So note down all these points, very, very important. I hope it is clear. Now, next, atomic and ionization enthalpy. Atomic and ionic radius. The atomic radii and ionic radii increases from top to bottom in the group because the atomic size decreases. Atomic size increases, so automatically the atomic radii. As the atomic size increases, the atomic radii and ionic radii also increases from top to bottom because of the increase in atomic number. As the atomic number increases, atomic size increases, so atomic radii as well as ionic radii also increases from top to bottom in the group. The order of atomic or ionic radius is oxygen less than sulfur, less than selenium, less than tellurium, less than polonium. Ionization enthalpy. Since atomic ionization enthalpy is nothing but what? The amount of energy required to move the valence electron. So that is called ionization enthalpy. So ionization enthalpy decreases from oxygen to polonium as the atomic size increases. So ionization enthalpy decreases down the group because it's easy to remove the valence electron from polonium and selenium and tellurium and compared to oxygen and sulfur. Since oxygen is having smallest atomic size, so automatically it is very difficult to remove the valence electron of oxygen when compared to sulfur, selenium, polonium, and sulfur, selenium, tellurium, and polonium. I hope it is clear. So the ionization enthalpy decreases from oxygen to polonium as atomic size increases. And the ionization enthalpy of group 16 elements are less than group 15. Very, very important point, because they do not have complete field. Why group 15 is having greater than? So group 15 elements are having more ionization enthalpy because they have half filled p orbitals, half-filled p orbitals. So half-filled p orbitals are more stable. So that's why the ionization enthalpy of group 15 elements is greater than group 14. It is greater than group 14 as well as group 16 also. Group 16. So the order will be like this: group 15, group 14, group 16, group 15, group 14, and group 16. So, and the order is group 15, then group 16, then group 14. So, for example, if they are given the question based on this, they can frame easily. Arrange the following in the decreasing order of the ionization enthalpy. Ionization enthalpy. So, they'll give nitrogen, oxygen, and group 14, that is carbon, as well as some other element, that is sulfur, for example. Let us take into consideration these four. So first is group 14, that is group 15, nitrogen, ionization to decreasing order greater than, then group 16, oxygen, then sulfur, then carbon. Oh no, sulfur will come later because it is coming in second group. So now, so this type of questions are important. First group 15 element, then group 16, then group 14 element, then second element in group 16, because they are given like this. So nitrogen greater than oxygen, greater than carbon, greater than sulfur. Why group 15 is having more ionization enthalpy? Because they contain half-filled p orbitals. Because the group 15 valence shell configuration is NS2, it is completely filled, and half-filled NP3. Because in P total 6 electrons is there, half-filled is there. So that's why group 15 elements ionization enthalpy is greater than group 14 as well as group 16. So please remember this point, very, very important. So the ionization enthalpy of group 16 elements are less than group 15 elements. Please note it down in your classwork. This is due to half-filled p subshell of group 15 elements, as already we discussed. So this is the trend of ionization enthalpy, and within the same group, that is group 16 only, if we take, the ionization enthalpy decreases from oxygen to polonium. as the atomic size increases. I hope it is clear. Next, electronegativity. Electronegativity decreases from oxygen to polonium because oxygen is electronegative, it is non-metal, that is non-metal. Sulfur is also non-metal. Selenium and tellurium are metalloids, and polonium is metal. So automatically for non-metals, electronegativity is more. That's why electronegativity decreases from oxygen to polonium. Oxygen is the second most electronegative atom in the periodic table after fluorine. First most electronegative atom is fluorine. Fluorine is the first most electronegative atom. Then second one is oxygen. Oxygen is the second most electronegative atom in the periodic table. So the top four elements with respect to electronegativity values are first fluorine, next oxygen, next nitrogen, next chlorine. This is based on Pauling scale. So oxygen is more electronegative than chlorine. Nitrogen is almost similar to chlorine. That's why nitrogen is more less electronegative than oxygen and fluorine. That's why when nitrogen combines with oxygen, it will attain positive oxygen state. So for example, here if you take into consideration 2x minus x is equal to 0, so x is equal to plus 3. So positive oxygen state. Why? Because nitrogen is, even though it's non-metal, but it is getting positive oxygen state because oxygen is more electronegative than nitrogen. Similarly, oxygen will attain positive oxygen state with the fluorine because if you take OF2, the oxygen state of oxygen is plus 1, sorry, plus 2, because it is plus 2. Oxygen is electronegative, but it attains positive oxygen state with fluorine because fluorine is more negative. The oxygen state of fluorine is always minus 1. So fluorine is more electronegative than oxygen. So that's why oxygen will attain positive oxidation state. So the top four elements with respect to electronegativity are fluorine, oxygen, nitrogen, and chlorine. I hope it is clear. Next. So within this group, the electronegativity decreases from oxygen to polonium. Next, electron gain enthalpy, the tendency. So the amount of energy released. What is electron gain enthalpy? The amount of energy released when a neutral gas atom gains electrons. It is called electron gain enthalpy. What is electron gain enthalpy? The amount of energy released when a neutral gas atom gains electron. So electron gain enthalpy generally decreases down the group because non-metals will have more electron gain enthalpy than metals. So the electron gain enthalpy of sulfur is higher than that of oxygen because it has empty d orbital. As it has empty d orbital, the electron gain enthalpy of sulfur is higher than that of oxygen because it can gain more number of electrons when compared to oxygen. This is due to small size of oxygen and the inter-electronic repulsions in oxygen. So the order of electron gain enthalpy of group 16 is very, very important because it is changing the trend. Oxygen is less than sulfur, sulfur is greater than selenium, tellurium, and polonium. So the order is simply direct. We can write sulfur is greater than oxygen, greater than selenium, greater than tellurium, greater than lead. So this is the electron gain enthalpy order of 16 group elements, decreasing order. Increasing order, you can write it. So this is polonium. Actually, it is not Pp. It is called polonium. So I'm writing it again. Usually you'll use Pp. That's why I'm writing like this, but it is polonium. So this is the electron gain enthalpy out of 16 group elements. That is sulfur greater than oxygen, greater than selenium, greater than tellurium, greater than polonium. I hope it is clear. So why this electron gain enthalpy of sulfur is greater than oxygen? Because in oxygen, due to its small size of oxygen and inter-electronic repulsions in oxygen, it is lesser than sulfur. And sulfur, it is higher because it has empty d orbital. Empty d orbital, so it can go up to maximum level. So that's why its electron gain enthalpy is more as it has empty d orbitals. Why? Because empty d orbital, because sulfur configuration is 3s2 3p4. 3s2 3p4, since it has 3 principal quantum number 3, so it has d orbital, empty d orbital. So due to which what happens, it can attract more electrons. So that's why electron gain enthalpy generally decreases down the group, but in this case, it is slightly different because sulfur is having empty d orbitals and due to small size of oxygen and inter-electron repulsions in oxygen, sulfur is having more electron gain enthalpy than oxygen. I hope it is clear. Next, physical properties of group 16 elements. The metallic character of elements of 16 group increases down the group. So the metallic character, any group, if you take the metallic character increases because down the group non-metal changes to metals, and in metallic group also down the group metallic character increases. So always in either if you take metallic group or non-metallic group, that is group 1, group 2, group 15, group 16, group 17, group 18, or group 13 and 14 also. In all the groups, the metallic character increases down the group. As I told you, sulfur and oxygen are non-metals, selenium and tellurium are metalloids, and polonium is a metal. So oxygen and sulfur are non-metals. Selenium and tellurium are metalloids, and polonium is a radioactive metal. Actually, you should write it here it as radioactive metal because radioactive means we'll study the radioactive elements in nuclear chemistry. We will not study under this. So radioactive metal. The melting and boiling points increases with an increase in the atomic number. As we go down the group, non-metals changes to metals. So automatically the melting points and boiling points are more for metals when compared to non-metals. That's why the melting point and boiling points increase with an increase in atomic number. Oxygen exists as diatomic gas, that is O2, dioxygen, whereas sulfur exists as polyatomic, that's why S8 molecule. S8 molecule, polyatomic. So oxygen exists as diatomic molecule and sulfur exists as polyatomic molecule because of its deconfiguration. It can form many compounds. Next, anomalous behavior of oxygen. Like in the group 15, we have anomalous behavior of nitrogen. In the same way, we have anomalous behavior of oxygen. Sorry, here oxygen. So the anomalous behavior of oxygen is due to its small size and high electronegativity. So why it is different from other elements? Because of its small size and high electronegativity. Oxygen can form strong hydrogen bonds in water, which is not found in other hydrates. If you take the hydrates of this group, so first oxygen hydrate, because the hydrate of oxygen is water, so it is having hydrogen bonds. That's why the boiling point is more. Whereas hydrogen sulfate, no hydrogen bonding. Hydrogen selenium, no hydrogen bonding. Hydrogen tellurium, no hydrogen bonding, and polonium anyway it is radioactive. So water is due to the presence of hydrogen bonds in water which is not found in other hydrates. Same you find in nitrogen also. Oxygen does not have d orbitals and hence its maximum covalency is 4. Actually the covalency of oxygen rarely exceeds 2. Usually it is maximum covalency is 4, but it is absolutely only 2 up to maximum 2 because there are no other compounds formed so far. I hope it is clear. Next, allotropic forms of group 16 elements. Oxygen has two allotropic forms, that is dioxin, that is O2, and ozone. We know ozone also. Sulfur has two allotropic forms, alpha sulfur, beta sulfur. And rhombic sulfur is more stable at room temperature. Alpha sulfur changes to beta sulfur at a temperature, transition temperature, that is 369 kelvins. So it is transition temperature, it forms beta sulfur. So that is called differences between alpha and beta sulfur, that is rhombic and monoclinic. So we have two allotropes of sulfur, that is rhombic sulfur and monoclinic sulfur. Very important these differences. They'll ask statement based question based on this statement based question. So alpha sulfur melting point is 385.8 kelvins, melting point is 393 kelvins. It is slightly higher than alpha sulfur. Specific gravity 2.06, 1.9. Specific gravity is less. Found by evaporating solution of whole sulfur in carbon dioxide, carbon disulfide, whereas prepared by melting rhombic sulfur in a dish and cooling till crystal is formed. So it is prepared from rhombic sulfur, alpha sulfur. If you heat alpha sulfur and cool it, then automatically beta sulfur is formed. I hope it is clear. Next, structures of S8 molecule. Both rhombic sulfur and monoclinic sulfur have crown shape, that is twin shape, crown shape. It has 8 SS bonds. How many SS bonds? 8. The SSS bond angle is 107 degrees. It is paramagnetic due to the presence of two unpaired electrons in antibonding pi orbitals. So this is there. So due to the presence of, so sulfur S8 molecule is paramagnetic, very very important. S8 molecule is paramagnetic due to the presence of two unpaired electrons in the antibonding pi orbitals. So this is called S8 molecule. So it is like crown shape. It has how many SSS bond angle is 107 degrees, and it has 8 SS bonds. 1, 2, 3, 4, 5, 6, 7, 8. So it has 8 SS bonds. I hope it is clear. Next, structure of SS molecule. On heating S8, it changes to hexa sulfur, that is S8, that is octatomic, this become hexaatomic, which on strong heating above 1000 kelvins form S2 molecule. This is more stable. So chair form, this is ground form, and this is boat form. So you get like this. You can see here, this is the boat form. Boat form or chair form is same, that is S6 molecule. It has 6 SS bonds. 1, 2, 3, 4, 5, 6. And bond angle is 1 or 2 degrees. Next, oxygen states. Group 16 elements exhibit very, very important. I told you already, oxygen states in all the groups are very important because based on the oxygen states, you'll get questions. So group 16 elements exhibit -2, +2, and +6 oxygen states. It will be exhibits -2, +2, and +6 oxygen, the common oxygen states except oxygen. Due to high electronegativity of oxygen, it shows only -2 oxygen states, except with fluorine, OF2 and O2F2, it shows +2 and +1. As I told you, oxygen shows positive oxygen state with fluorine. With fluorine, it forms two compounds, that is oxygen difluoride and dioxygen difluoride. Dioxygen difluoride, oxygen state of oxygen is +1, and oxygen difluoride, oxygen state of oxygen is +2. Apart from this, oxygen will show only -2 oxygen state, and with peroxide bond it shows -1. With superoxide it shows -1/2. So with superoxides like KO2. So that all we'll discuss based on oxidations. So sulfur, selenium, and tellurium usually show +4 and +6 oxygen states because of their empty d orbital. As they contain d configuration, they can show oxygen states not only +2. Sulfur will show -2. Sulfur will show -2 because in H2S it is -2. It shows +2. It shows +4 and +6. So it shows all these oxygen states. And selenium and tellurium being metalloids, they'll show only +2, +4, and +6 oxygen states. So these are the common oxidation states exhibited by these elements. Oxygen will show -2, -1 in case of peroxy bonds, +2, +1 with respect to fluorine. Apart from that, it shows -1/2 with superoxides, that is KO2. If you take KO2, it shows -1/2, -1/2. So I'm writing it again. The oxygen state of oxygen in KO2 is -1/2. So I hope it is clear. So these are the oxygen states exhibited by these elements. Next, hydrates of group 16 elements. Group 16 elements forms hydrates of type MH2, where M is called element of group 16. Example, water, hydrogen sulfide, hydrogen selenium, hydrogen tellurium, and hydrogen polonium. Polonium, it is rare, it will not form usually. So, trends in properties of hydrates. Thermal stability, MH bond enthalpy, bond angle and basic nature decreases from water to hydrogen tellurium hydride. So the thermal stability, MH bond enthalpy, bond angle, and basic nature decreases from water to tellurium hydride. Very, very important. So shape of water, it is V shape. It is undergoing sp3 hybridization. All the hydrates will undergo sp3 hybridization, but the shapes are different. So hydrogen sulfate, the shape is sp3. So hybridization is sp3. Shape is again angular. So hydrogen selenium hydride, tellurium hydride. So 91 degrees, 90 degrees. So as we go down the group, the thermal stability, MH bond enthalpy, bond angle, and basic nature from water to hydrogen tellurium decreases from water to hydrogen tellurium. So these points are very important because they ask examination. Write the thermal stability order of hydrates of 16 group elements. So hydrates of 16 group elements, thermal stability order. Water is greater than hydrogen sulfide, greater than hydrogen selenium hydride, greater than tellurium hydride. So this is the order. Not only for thermal stability, this is the order for MH bond enthalpy, this is the order for bond angles, and also the basic nature. So all the four properties, this is the decreasing order of hydrates of 16 group elements. So very, very important. Next, trends in properties of hydrogen hydrates. Continuation. Acidic character, MH bond length, and reducing property increases from water to hydrogen, MH bond length. And here H2O to hydrogen tellurium, tellurium hydrate. The order of boiling points of hydrates of 16th group, usually water greater than hydrogen tellurium. This is very important because the order is somewhat different because tellurium is metalloid and selenium is metalloid and sulfur is non-metal and water. But due to presence of intermolecular hydrogen bonding, this is higher than all others. So this order is very, very important. So the order of boiling point of hydrates of 16th group elements follows the order: water greater than tellurium hydrate because being a metalloid, greater than selenium hydrate, again metalloid, and greater than hydrogen sulfate, it is non-metal hydrate. So this is the order. Even though oxygen and hydrogen is also non-metallic hydrate, but due to the presence of intermolecular hydrogen bonding, water has higher boiling point than rest of hydrates and exists as liquid at room temperature due to intermolecular hydrogen bonding. So due to this, water boiling point is 100 degrees C. The boiling point of water is how much? 100 degrees C. So that's why this is a trend. So whenever you have different trends than the regular trend, that type of trends they'll ask in the examination. I hope it is clear. Next. Dihalides like OF2, SCl2 have angular shape with sp3 hybridization, and SCl2 is prepared from S2Cl2. Halides of group 16. Now halides of group 16. Group 16 elements forms dihalides mainly with oxygen and sulfur. They have angular shape with sp3 hybridization. Not only oxygen will form only dihalides, but others will form tetrahalides and hexahalides also. Like in case of sulfur, it forms SF6 and SF4 also. So the hybridations in these are different. So dihalides we are discussing about OF2 and SCl2 have angular shape with sp3 hybridization. Sulfur dichloride is prepared from thionyl chloride S2Cl2 and chlorine. So S on when combines with chlorine with limited of chlorine, it forms S2Cl2, which on excess of chlorine will form SCl2, dark red liquid. Monohalides like O2F2, S2Cl2 have open book structure. All these are very important. Monohalides, that is O2F2, S2Cl2 have open book structure. These monohalides undergo disproportionation reaction. So if it takes Se2Cl2 undergoes SeCl4 and Se. Here the oxygen state of selenium is 0, here it is +4, and here it is +1. So +1 changes to +4, that is increase in oxygen state, and +1 changes to 0, that is decrease in oxygen state. So selenium diselenium chloride, that is monohalides, undergo disproportionation reaction. Dihalides will not undergo disproportionation reaction. What is disproportionation? Already we know disproportionation reaction is nothing but for the same element simultaneously oxidation and reduction takes place in a given reaction. So selenium is an element which is undergoing oxidation as well as reduction. I hope it is clear. Next, oxides of elements of group 16. Elements of group 16 forms two types of oxides. So in addition to these halides, we'll discuss more. So elements of group 16 forms two types of oxides, MO2, that is dioxides, and MO3, trioxides. So sulfur dioxide, selenium dioxide, tellurium dioxide, and trioxide, sulfur trioxide, selenium trioxide, tellurium dioxide. Reducing property of dioxides increases from sulfur dioxide to tellurium dioxide. Very, very important. The reducing property. Sulfur dioxide is acidic in nature. Tellurium dioxide is amphoteric in nature. So these oxides. So order of acidic strength, sulfur dioxide is acidic, then lesser, then less. Acidic strength of trioxide, sulfur dioxide is more acidic. So reducing property decreases from sulfur dioxide to tellurium because tellurium oxide is metalloid. So that's why it is reducing property is more. It is reducing property is greater than sulfur dioxide or selenium dioxide. So tellurium dioxide reducing property is greater than selenium dioxide, greater than sulfur dioxide. Same in the case of trioxides also. I hope it is clear. So they form basically sulfur dioxide, dioxides and trioxides. Now, why H2S is acidic while H2O is neutral? H2S is a stronger acid than H2O. Hydrogen sulfide is acidic. Why? Because, let us see now, the SH bond is weaker than OH bond in hydrogen sulfide. That's why it is acidic in nature. And as SH bond is easily being changed, is can be the bond dissociation enthalpy is less, so that's why it is H plus ions it can release easily, so that's why it is acidic. While water is neutral, and H2S is a stronger acid than H2O because of this reason. Next, halides of group 16 elements. Group 16 elements form halides of type. Very, very important. As I told you, halides, they form halides of type MX2, MX4, and MX6 type of halides. Only sulfur, selenium, and tellurium will form these halides. And oxygen will form only among different halides of group 16 elements. Hexafluorides are stable and gaseous in nature. Hexafluorides, that is MX6, that is SF6 example. SF6, SCF6, and TEF6. These are hexafluorides. These are stable and gases at room temperature and gases in nature. They have octahedral shape due to the sp3 what is the hybridation in this? sp3d2 hybridation present in this. So of central element, and they have octahedral structure with a zero lone pairs. Zero lone pairs, no lone pairs, zero lone pairs, because all the as sulfur has 6 electrons, so 1, 2, 3, 4, 5, 6. So all the fluorines will attack this sulfur. So due to which what happens, they have 6 valence electrons. So 6 electrons will be shared by 6 fluorines. That's why the shape is octahedral. So they do not have, they have lone pair of electrons. Let us see now. So this is a SF6 molecule. It is octahedral in shape. So usually what type of halides they'll form? They'll form halides of type MX2, MX4, and MX6. Oxygen will form only one type of halide, that is O2F2 and OF2. Apart from this, oxygen will form O2F2 and OF2. That's all. No other halides will be formed by oxygen because of its highly electronegative nature. Tetrahalides of group 16 elements. Among tetrafluorides group of 16 elements, SF4 can't be prepared by direct combination of elements as it forms SF6 easily. SF4, that is sulfur tetrafluoride, is prepared by the combination of SCl2 and Cl2 with NaF. In SF4, the sulfur atom is sp3 hybridized. Sulfur atom is what? sp3 hybridized and has a seesaw geometry due to lone pair. It has one lone pair of electrons. Has one lone pair of electrons, so that's why it will not take regular shape like sp3 hybridization. Due to sp3, actually sp3d hybridization means it should have a regular shape, but due to the presence of one lone pair of electrons, it will take seesaw geometry. So this is called seesaw geometry. You can see here, this is called seesaw geometry. SF4, as I told you, it contains one lone pair of electrons. So hexafluorides, no lone pairs. Tetrafluorides have lone pair of electrons. So next, we'll continue with this general trends in periodic properties. So let us see now. Apart from this, we'll have more properties of general trends, that is sulfate, halides, oxides, and hydrates. More properties we'll see in this of group 16. Order of electron affinity: sulfur, selenium, tellurium, polonium, and oxygen. All these points are important. These are additional points which I have designed for you, especially for objective exams. Order of electron affinity 1 or electronegativity 1. Very important point. Electronegativity of oxygen is negative, while electronegativity of EA2 of oxygen is positive. Means what? We can remove 2 electrons from oxygen. So this O2 minus, this is electronegativity of 2. Electronegativity of 2 oxygen is positive, and the ionization potential and electronegativity decreases down the group. So here electron affinity of oxygen is negative, first electron affinity, whereas when it accepts 2 electrons, the second electron affinity of oxygen is positive. Very, very important point. So electron affinity means the amount of energy released during the gaining of electrons by a neutral gas atom. So that is called electron affinity. So electron gain enthalpy, both are same. Electron affinity means when oxygen gains 1 electron, it is nothing but electron affinity 1. Electron affinity 1. When oxygen gains second electron, it is called electron affinity 2. And electron affinity 1 is negative because it is exothermic pulse, whereas electron affinity 2 is positive because it is endothermic process. So the electron affinity, second electron affinity of oxygen is always positive. Remember this point. And the electron affinity values of 16 group elements follows the order: sulfur, selenium, tellurium, polonium, and oxygen. So which is highly, this is the order. Ionization enthalpy and electron negativity decreases down the group. Radius, density, melting points, and metallic nature increases down the group. So the atomic radius, density, melting point, boiling points, metallic nature increases down the group. This already we know. And tendency to form pi bonds decreases down the group. Only pi bonds will be formed by oxygen, not even sulfur also. Sulfur also can form pi bonds, but other elements in this group do not form pi bonds, only single covalent bond. So that's why the tendency to form pi bonds decreases down the group. This is the additional material which I have given for you. Next. So oxygen cannot show positive oxygen states +6 due to absence of d orbitals. Polonium shows only +2 and +4 oxygen states, very, very important points. Polonium will show only +2 and +4 oxidation states. Down the group, stability of +6 oxygen state decreases while that of +4 increases due to inert pair effect. So what is inert pair effect? The reluctance of s orbital. So that's why +4 increases and +6 decreases down the group. In +4 and +6 oxygen state, the substance is more covalent due to high polarization. I hope it is clear. So +4 state is more stable down the group. +6 oxygen state stability decreases while that of group 4 +4 oxygen state increases due to inert pair effect. For example, SCX4 is more stable than XCX6. I hope it is clear. Next. Trends in halides of group 16, more additional points. The stability of halide of an element decreases in the order F minus, chlorine minus, Br minus, iodine minus. Among hexahalides, hexafluorides are only stable. Remaining hexachlorides, bromides, and iodides, they are not formed. Even if they form also, they are not stable at all. So SF6 is more stable than SCl6, SBr6, Si6. Usually they will not form. Among hexahalides, hexafluorides are only stable, and SF4 is a gas, SCF4 is a liquid, and TEF4 is a solid. SF4 is sulfur tetrafluoride is a gas, selenium tetrafluoride is a liquid, and tellurium tetrafluoride is a solid. Sulfur tetrafluoride is a fluorinating agent. Sulfur tetrafluoride is a fluorinating agent. All elements except selenium form dichlorides and dibromides only. They will not form tetrachlorides and tetrabromides. S2Cl2 reacts with ethylene to give mustard gas. This is very, very important. Sulfonyl chloride reacts with the ethylene. Ethylene means C2H4 and forms mustard gas. So this mustard gas formula you can verify in organic chemistry. I hope it is clear. Next. See, these are the trends in halides of group 16 elements. Let us see now next. Dioxygen. Now preparation of oxygen. Oxygen is paramagnetic liquid. Liquid oxygen is pale blue with while solid oxygen is deep blue in color. So now preparation of chemical properties are over. So we are doing now preparation. Oxygen is paramagnetic, liquid oxygen is pale blue while solid oxygen is deep blue in color. Mixture of N2H4 and oxygen is used as rocket fuel. Oxygen oxidizes P4 to P4O10 and zinc sulfide to zinc oxide and sulfur dioxide. Oxygen reacts with HCl in CuCl2 to give chlorine. This process is known as Decaun's process. So oxygen combines with HCl. So these things we'll discuss anyway in the preparation of oxygen. So oxygen combines with HCl and forms chlorine gas and water. So this is the preparation, the presence of copper chloride, that is cupric chloride. This is called Decaun process. This will study in halogen family. So oxygen is paramagnetic because it contains lone pair of electrons, and liquid oxygen is pale blue color, while solid oxygen is deep blue in color. Mixture of hydrazine, that is N2H4 and oxygen, is used as rocket fuel. Oxygen oxidizes P4 to P4O10 and zinc sulfide to zinc oxide and sulfur dioxide. Oxygen reacts with HCl. This process in the presence of copper chloride to give chlorine gas. This process is known as Decaun's process. Next, oxygen forms oxides with metals, non-metals, and metalloids. They form oxides with metals, metallic oxides, non-metallic oxides, and metalloids. And metallic oxides usually they are basic in nature. Metallic oxides are basic in nature. Usually non-metallic oxides are acidic in nature. And amphoteric oxides, these are nothing but amphoteric in nature. Metalloid oxides are amphoteric in nature. Please note down this point, very important. So type 1 based on oxygen state of oxygen, and type 2 based on the nature of oxides. So oxygen forms oxides with metals like sodium oxide, potassium oxide, and so on, and magnesium oxide, etc. So metallic oxides, aluminum oxide, like that. So metallic oxides are basic in nature, and non-metallic oxides like sulfur dioxide, nitrogen dioxide, etc. So carbon dioxide, all these are non-metallic oxides. These are acidic in nature, and metalloid oxides like, what are the metalloids we have in the 15th group? We have, what are the metalloids? Nitrogen, phosphorus, arsenic oxide. So arsenic oxide and selenium oxide, selenium dioxide, etc., tellurium dioxide, etc. So all these are called amphoteric oxides. These are called metalloid oxides are amphoteric in nature. So oxides are broadly classified into two types based on the oxygen state of oxygen, and second one based on the nature of oxide. Let us see now two types of oxides. Normal oxides, they have normal MO bonds. Oxygen state of oxygen is -2. This already we know. In most of the oxides, the oxygen state of oxygen is -2. That is normal oxides. In peroxides, oxygen state of oxygen is -1. It is diamagnetic in nature. Peroxides contain O2 2 minus ions. Ionic peroxides contain what? O2 2 minus. So it is diamagnetic because oxygen atom is 8 electrons. So it is gaining 2 electrons, means automatically it becomes 10 electrons. So it is all paired up. So due to which what happens, it is diamagnetic. And the oxidation state of oxygen is -1 in peroxides. Superoxides, oxygen O2 minus is paramagnetic. In superoxide, it is nothing but O2 minus. O2 minus is paramagnetic in nature. Oxygen state of oxygen. Oxidation state of oxygen is -1/2. Only first group metals and second group metals will form superoxides, like potassium will form superoxide. In first group also, sodium will not form superoxide. Potassium, so sodium, potassium, rubidium, and cesium will form superoxides. So rubidium superoxide, cesium superoxide. Only this will form superoxide. Sodium will not form superoxide. So the oxidation state of oxygen in superoxides is -1/2. Suboxides, carbon suboxide, it will have less than. So they have bonds and MO bonds. They contain less oxygen than expected. So it is fraction. In suboxide, it is fraction. Very, very less. So these are the different types of oxides we have. All these points are very important for objective. Please note it down. Next, we have basic oxides, acidic oxides, amphoteric oxides, neutral oxides. All are very important. Which of the following is basic? And the following oxides in the increasing, decreasing order of their basic character, increasing, decreasing order of their acidic character, amphoteric oxides, and neutral oxides. So generally, briefly, I'll tell you. So what are basic oxides? Metallic oxides are basic in nature. Metals in lower oxygen state. Metallic oxides are basic in nature, in which these points you please note down, in which metal has lower oxidation state. So first group and metal, second group metallic oxides are basic in nature, and D block elements are, already D block elements are all metals. Those metals can be acidic or basic based on the oxygen state of metal. For example, manganese oxide. The oxygen state of manganese is +2. It is basic in nature, highly basic. Whereas Mn2O7, manganese dimanganese heptoxide, it is acidic in nature because the oxygen state of manganese is +7. So higher oxygen state of metals will have acidic nature, lower oxygen state of metals will have basic in nature. So, and acidic oxides, usually non-metallic oxides are acidic in nature. Non-metallic oxides are acidic in nature. Amphoteric oxides, there is nothing but zinc oxide, aluminum oxide, some metals which have empty orbitals, along with metalloid oxides like selenium dioxide, etc. All these are amphoteric oxides. Neutral oxides, non-metallic oxides in which non-metallic oxides, these points are very, very important. Please note down. Non-metallic oxides in which the non-metal is in lower oxygen state, in which the non-metal is in lower oxidation state. They are said to be neutral oxides. Lower oxidation states. Example, CO, carbon monoxide, the oxidation state of carbon is +2, and NO, nitrogen monoxide, it is +2 again. N2O is neutral again because oxygen state of nitrogen is +1 only, etc. So if the non sulfur dioxide, sulfur trioxide, they are acidic, whereas sulfur monoxide is neutral oxide. So the what are neutral oxides? Non-metallic oxides in which the non-metal is in lower oxygen states. They are not said to be neutral oxides. And acidic oxides like carbon dioxide, sulfur trioxide, etc. So where the non-metals are in higher oxygen states, non-metallic oxides which are in higher oxygen states are said to be acidic oxides. And basic oxides, usually almost all the metallic oxides are basic, in which the metal is in lower oxygen state. And if the metal is having higher oxygen state than expected, they are supposed to be acidic. I hope it is clear. So these are the different types of oxides, classification based on the oxides, basic oxides, acidic oxides, amphoteric oxides, neutral oxides. Please note down all these, very, very important. I hope it is clear. Next. So what are basic oxides? These are metal oxides, first year group and second year group metals, as I told you. First group metals and second group, that is lithium oxide, sodium oxide, rubidium oxide, potassium oxide, etc., and magnesium oxide, calcium oxide, barium oxide. All these first year group and second year group metals and lanthanides form basic ionic oxides. They are ionic in nature and they are also basic in nature. These oxides react with water to give hydroxides. So any first group metals or second group metals oxides, if you dissolve in water, they form hydroxide. That's why they are basic in nature. Some metal form oxides in different oxygen state. The oxide with the lowest oxygen state of metal is ionic and most basic. As I told you, the oxide with the lowest oxygen state of metal is ionic and most basic, and the oxide with highest oxygen state of metal is covalent and it is not basic, it is acidic. Example, like in the case of manganese, I told you. These are non-metallic oxides and are covalent in nature. Non-metallic oxides are acidic oxides. They have low melting points and boiling points. Oxides of boron, B2O3, silicon dioxide form giant molecules and they possess high melting points and boiling points. Silicon dioxide is insoluble in water. It reacts with bases. Some metal oxides in higher oxygen state also forms acidic oxides, as I told you. Some metal oxides in high oxygen states like Mn2O7, Cr2O7. These are all acidic oxides, even though they are metals and non-metal combination, but still they are acidic oxides, and most probably they are also covalent in nature. Next, amphoteric oxides. They react with both acids and bases. Hence, they show both acidic character as well as basic character. So, beryllium oxide, Al2O3, gallium oxide, gallium oxide, tin oxide, Sb2O3, PbO, zinc oxide, chromium oxide. All these are nothing but they are anyway. Metalloid oxides are metalloid antimony oxide, selenium oxide, etc. All these oxides are anyway they are amphoteric. Apart from that, some metallic oxides are also called as amphoteric because they combine with both acids and bases and forms compounds. Aluminum oxide, it forms aluminum hydroxide, and aluminum oxide, it forms Al2H2O taken 6 times. Lead oxide, it forms lead nitrate plus water. Lead oxide with sodium hydroxide forms Na2P. So it is base and this is acid. This is base, this is acid, and so on. I hope it is clear. With H plus, it is called acid. With OH minus, it is called base. So these oxides combine with acid as well as base and forms compound. That's why they are called as amphoteric oxides. Neutral oxide. These oxides are covalent in nature. These are neither acidic nor basic. Example, as I told you, non-metals in their lower oxygen states. The oxygen state of nitrogen is here. How much? It is only +1. It is +2, and it is +2 for carbon. And water, it is oxygen is -2. So the non-metal oxides in their lower oxygen states are neutral. They are neither acidic nor basic. So in the lower oxygen states, non-metals in their lower oxygen states, non-metals in their lower oxidation states are basic in nature. Sorry, neutral in nature. Neutral means they are neither acidic nor basic. I hope it is clear. Note down this point, very, very important. Next, we have ozone. The oxygen will have two allotropes, that is, one is oxygen and another is ozone. Ozone is the allotropic form of oxygen and is also treated as the oxide of oxygen. Ozone is diamagnetic in nature. Ozone is what? Diamagnetic in nature because all are paired up. In high concentrations, it is dangerously explosive. Nitric oxide released from supersonic jet planes deplete the ozone layers. So nitric oxide plus ozone forms nitrogen dioxide and oxygen gas. So they deplete the ozone layers. Now, oxidizing properties of ozone. Due to the liberation of nascent oxygen, because ozone liberates what? Nascent oxygen, just one oxygen, which is highly reactive. Ozone behaves as a good oxidizing agent. It can bring oxygen to any other element, to all the elements, and it's a dry bleaching element, bleaching agent. It's a dry bleaching agent. Ozone on reaction with hydrogen sulfide forms sulfur plus oxygen plus water. Ozone on reaction with hydrogen bromide. So it oxidizes hydrogen bromide to bromine. It oxidizes hydrogen sulfide to sulfur. It reduces, actually, it should, we can say it oxidizes. Ozone oxidizes sulfur to sulfuric acid. Ozone oxidizes ferrous sulfate to ferric sulfate. Ozone oxidizes mercury to mercuric oxide, which is also called as tailing of mercury. What is tailing of mercury? They'll ask in the examination. Ozone on reaction with mercury will form silver. Silver is coated on it due to the formation of mercuric oxide, which is called as tailing of mercury. That's why this mercury is used as thermometric liquid. Very, very important. What is tailing of mercury? When ozone combines with mercury, it forms mercuric oxide along with oxygen gas, and this mercuric oxide will be sticking on the glass. So that's why it is called tailing of mercury. It oxidizes potassium ferrocyanide to ferricyanide. So ozone is a good oxidizing agent. It brings about oxidation to others and itself undergoes reduction. Ozone reacts with potassium hydroxide to form potassium ozonide, KO3. It combines with potassium hydroxide to form potassium ozonide. And KO3 is KO3 is orange colored solid in which O3 minus is paramagnetic due to the presence of unpaired electron. So KO3 is orange colored solid in which O3 minus is paramagnetic due to the presence of unpaired electron. Next, we'll discuss about sulfur. So we have completed about oxygen. Now we'll discuss about sulfur. Rhombic sulfur and monoclinic sulfur, already we know they are soluble in carbon disulfide. At high temperature, that is greater than 1000 degrees C, sulfur is the dominant species. Like oxygen, sulfur has two unpaired electrons in the antibonding orbitals and hence it is paramagnetic in nature. Oxygen is also paramagnetic in nature, and also sulfur is also paramagnetic in nature because they contains unpaired electrons in antibonding orbitals. What is anti-bonding and bonding? That we'll be discussing already, you know, no, because you're in 12th class, that is in molecular orbital theory of chemical bonding. Next, sulfur dioxide reducing properties. Sulfur dioxide is a good reducing agent. It reduces halogen to halogen acids. The chlorine changes to HCl by means of sulfur dioxide. It reduces acidified potassium iodate to iodine. Potassium iodate changes to iodine. So by means of sulfur dioxide, it reduces ferric salts to ferrous salt. This is called ferric salt. That is Fe2SO4 taken this ion in plus 3 state. Here in this ferric means ferric means ion in plus 3 state, and ferrous means ion in plus 2 state. So it reduces ferric salts to ferrous salt. It decolors pink color of acidified potassium permanganate solution. Pink color to colorless. So potassium permanganate changes to manganese sulfate. So it decolors, it reduces potassium permanganate to manganese sulfate. I hope it is clear. So this is called the reducing properties of sulfur dioxide. All these reactions are important. It reduces potassium dichromate orange color to chromium sulfate, that is green color. So potassium dichromate solution on reaction with sulfuric acid along with sulfur dioxide, it forms potassium sulfate, chromium sulfate along with water. So orange color solution changes to green color solution. So sulfur dioxide is a good reducing agent. Moist sulfur dioxide will act as bleaching agent. Sulfur dioxide acts as bleaching agent. Its bleaching action is due to reduction. During bleaching, sulfur dioxide converted into H2SO4 and it releases nascent hydrogen. So this is the bleaching action of sulfur dioxide. Again, I'll explain. So sulfur dioxide with water it forms sulfuric acid along with nascent hydrogen. This nascent hydrogen attacks coloring matter and makes it colorless. Coloring matter. It attacks coloring matter, that is called bleaching action, and makes it colorless. So the bleaching action of sulfur dioxide is temporary because it again once the it is exposed to sunlight, it can be again regained. The color is regained back. So that is why it attacks. Bleaching action of sulfur dioxide is converted into H2SO4. This sulfur dioxide when react with water, it forms moist sulfur dioxide. It forms sulfuric acid along with nascent hydrogens. These nascent hydrogens are just one hydrogens are most reactive. They attack the coloring matter of the material, which makes them colorless. And the color is regained once it is removed, once it is exposed to sunlight. I hope it is clear. So this is called bleaching action of sulfur dioxide. Sulfur dioxide properties. Sulfur dioxide also behaves as an oxidizing agent. Sulfur dioxide is neither combustible nor support of combustion. However, burning magnesium heated carbon continues to burn in sulfur dioxide. Sulfur dioxide reacts with PCl5. This reaction already we have seen. It forms SOCl2 along with POCl3. This SOCl2 is used in the preparation of mustard gas. This SOCl2 threonyl chloride is used in the preparation of mustard gas. So sulfur dioxide combines with phosphorus pentachloride and forms SOCl2 threonyl chloride along with POCl3. These reactions already we have seen in phosphorus threonyl chloride. This is called threonyl chloride. This is not mustard gas. It's used in the preparation of mustard gas. I hope it's clear. Next, sulfur trioxide. At room temperature, sulfur trioxide is a solid. This is the structure of alpha and beta forms of sulfur trioxide, and gamma form of sulfur trioxide is this. The gamma form of sulfur trioxide is cyclic and trimite. Trimite means what? Three molecules combined together. It is S3O9. It can be taken as S3O9. S3O9. You can see here S3O9, 9 oxygen atoms. Alpha and beta forms of sulfur trioxide. This is the structure of sulfur trioxide. It is polymeric in nature and shape is linear. Next, trends in hydrides of group 16 elements. Water has highest boiling point, exists as liquid due to intermolecular hydrogen bonding, and H2O is not a reducing agent. It is neutral. Dipole moment of water is higher than that of remaining hydrides because of intermolecular hydrogen bonding. They have dipole also. Dipole moment. Dipole moment is determined by the letter mu. So dipole moment is nothing but what? The migration of electrons towards more electronegative atom. So from this hydrogen and from this dipole moment existing. So this is the symbol of dipole moment. So dipole moment is there for water, but it is not there for hydrogen sulfide, selenium hydride, tellurium hydrate, etc. No dipole moment. No dipole moment. Next, hydrogen sulfide. Hydrogen sulfide is a weak dibasic acid. Dibasic because it contains two H2 hydrogens, two replaceable hydrogens. That's why it is a weak dibasic acid. It is strong reducing agent. It reduces FeCl3 to FeCl2. Hydrogen sulfide combines hydrogen peroxide and forms water and sulfur. Potassium permanganate to manganese sulfate. So it is a good reducing agent. Hydrogen sulfide continued. Hydrogen sulfide is used as analytical reagent for the inorganic salt analysis. Analytical reagent. Hydrogen sulfide reacts with metal salts forming corresponding sulfides. The metal sulfides can be divided into three groups. Sulfides precipitated in acidic medium. So these are very important for IIT advance. The metal sulfides can be divided into three groups. Sulfides, which is precipitated in acidic medium, that is cadmium sulfide, arsenic sulfide, antimony sulfide, lead sulfide. These are all forms precipitates in acidic medium. Sulfides precipitated in basic medium, zinc sulfide, cobalt sulfide, nickel sulfide, manganese sulfide, and sulfides which are not precipitated in any medium. Chromium sulfide, aluminum sulfide, magnesium sulfide, barium, strontium, calcium, potassium, and sodium. So that's why this hydrogen sulfide is reacts with metal salts, forming corresponding sulfides. These metal sulfides can be divided into three groups: the sulfides which is precipitated in acidic medium, the sulfides which is precipitated in basic medium, and the sulfides which will not precipitate in any medium. So these are the different types of sulfides we have. Next, trends in oxoacids of group 16 elements. The pi bond in M double bond O of oxyacid is p pi d pi bond. As the size of metal increases, that is element metal increases, not only metal increases, MO bond decreases, the size of MO bond decreases. That's why only sulfur will form double bonds, whereas other elements will not form double bond. H2S2O3 is not stable and does not exist in aqueous medium, but exists in ether medium. H2SO3 sulfurous acid can act as reducing agent. In water, H2SO2O8, Marshall's acid gives H2SO4 and H2SO4 is called Caro's acid. So all these things we'll discuss in oxy acids of sulfur. This year we have given traits. Next, sulfuric acid. Concentrated sulfuric acid is also known as oil of vitriol. As I told you, sulfuric acid is also called as king of chemicals. Why it is called king of chemicals? Because based on the usage of sulfuric acid in the industry, we can say about the production. Because of all the products we use definitely sulfuric acid. That's why sulfuric acid is also called as king of chemicals. So it is also known as oil of vitriol. Sulfuric acid forms hydrate with water and large amount of heat is liberated. Sulfuric acid is less volatile, so it displaces more volatile acids like HCl, HF, HNO3 from their salt solutions. Concentrated sulfuric acid is a moderate oxidizing agent. It is also a dehydrating agent. That's why this sulfuric acid can absorb water. So it is also called as dehydrating agent because in organic chemistry reactions from sulfuric acid is used as dehydrating agent. Concentrated sulfuric acid strong dehydrating agent due to its high affinity towards water. It absorbs water. That's why concentrated sulfuric acid is a strong dehydrating agent. Oxygen in nature, sulfuric acid dissociates to form hydrogen water, sulfur dioxide, nascent oxygen. This nascent oxygen is highly reactive. It oxidizes carbon to carbon dioxide, sulfur to sulfur dioxide, phosphorus to phosphoric acid. Reaction with metals, copper changes to copper sulfate, silver changes to silver sulfate because these are all nothing but redox reactions, oxidizing nature of sulfuric acid. So this is the additional material. More about group 16 elements we'll discuss later on. I hope you understood all the points. What are the points I have marked? It is important. Please note down that, and we'll do questions finally after finishing all the topics. Thank you.